So we're going to take a look here at one method of solving systems of linear differential equations. This is called method by elimination or systematic elimination. Okay. And in general, a system of n linear ordinary differential equations with n unknowns. So you would expect to have n equations for n unknowns to constrain the system and get solutions that are constrained, and there's sufficient amount of information to constrain each of the variables. So all of these are ordinary differential equations because they depend only on the variable t. So n different functions or dependent variables, and they all depend on just one variable. So we are in the domain of ordinary differential equations. Now what are these p's? Well, each equation can have a polynomial with the operator d, okay? A polynomial of like any arbitrary degree. It could be less than n, it could be greater than n, it doesn't matter. So these are polynomials in the differential operator, and each equation has a polynomial for each unknown, okay? And of course they're linear, so we could do this. If the equations were nonlinear, then we would not be able to write it out like this, okay? A solution of a system of differential equations is a set, okay, so you get some function of phi of t for each of the unknown or dependent variables, phi1 for x1, phi2 for x2, that satisfy each of the equations in the system on a common interval. So each term here, each solution for each of the dependent variables must satisfy all, okay, simultaneously, all of these equations, all n equations, when you plug all of the unknowns in, okay? So that's important. You can't just satisfy one of them. Even if, say, just one equation has just one of the unknowns, okay, but it shows up in other places, well, it has to satisfy all of the equations. The method of systematic elimination involves applying the differential operator and taking linear combinations of the system so as to decouple dependent variable relations into equations that depend only on one dependent variable. And that's just a kind of overview that sort of makes more sense to actually look at this in practice, what we mean by it. Okay, so let's look at an example. So here we have this simple system, okay? Two differential equations, two dependent variables, of course ordinary because they only depend on t. dx dt is equal to 3y and dy dt is equal to 2x. Now we could rewrite this system in terms of the operator d. So, instead of d dt, we have this d. It just kind of makes things easier to operate on when you rewrite it in this form. We're going to call this first equation equation 1 and the second equation equation 2. So we're going to take equation 1 and operate with the operator d, the differential operator. And when you operate with d, you get this. But now wait a second. We have ourselves a dy right there. So why don't we solve for dy in equation 2 and plug it into this equation up here that we got from operating with d on 1. Okay, so this dy is equal to 2x, and we're going to plug it into that first equation, and we get, when we substitute for dy 2x, we get this equation here, okay? And look, this is what's meant by decouple, okay? Each of these equations had an x and a y in it, and now we're left with an equation that only depends on, that only has x in it, okay? So that's what's meant by this systematic elimination. So solving in a straightforward way here is to solve this, it's a homogeneous equation. So we get the two distinct real roots for the auxiliary equation, we have this general solution. Now note that something we could do at this point is take this solution and just plug it in to the second equation and integrate this dy term to arrive at y. Okay? But we could also do something else. We could, kind of be more symmetric about how we're treating x and y. And we could operate it with 2 on d, with d, the differential operator on 2, and we get this equation. And notice what's happening here. We're trading first order equations for second order ones. And we get to substitute that dx with, guess what? What's in equation 1. Okay? So we plug equation 1 into this this equation here. And instead of dx, we now have 3y, which is coming from solving that for dx. And we end up with this second order equation that only has y in it. Okay, so we've decoupled x and y. This gives the auxiliary equation that we see here, which is, coincidentally the same as the one with x. And we solve for y. And now one might think, okay, well, I got a relation for y, I got an equation for x, I'm done. But you're actually not. This is a system, okay? Each of these solutions has to satisfy all of the equations, not just one. And so when we took linear combinations, okay, we lost some information when we decoupled. And now we're going to regain that information by plugging in our solutions into the equations. So if we take x, we take its derivative. So we found x. We take the general solution for x, we take its derivative, and we plug that into here. We get what you see here, okay? And that simplifies to this when we gather terms. And the only way that this is 0 is for each of these coefficients to be 0. And so we end up with this relation between C3 and C1 and C4 and C2. Those constants were not independent, okay? There was not 4 degrees of freedom. There are actually only 2 degrees of freedom for this system of 2 equations with 2 unknowns, first order system of 2 equations with 2 unknowns, okay? And so we could substitute what we found for C3 and C4 back here, and notice now that x was unchanged, right? But y2 now has C1 and C2, okay? So we actually only had 2 degrees of freedom in the sense that there was, there's flexibility in varying C1 and C2 independently, but you could not vary all 4 of those constants of integration, those constants that we got from solving the equations independently. You could not. Now, someone might say, well, what if I took y, okay, the solution for y, which we found here, took its derivative and plugged it into 2 instead? Well, you'll get the same constraints, okay? The algebra might be slightly different, but you're going to arrive at the same exact constraints. So it actually doesn't matter, okay? And now we're sure that our solutions respect these 2 equations simultaneously. So let's look at another example, and here we'll have a non-homogeneous equation in the mix, so it's a bit more involved, and we also have one equation that's second order and another that's first, okay? So we want to solve that, so we're going to rewrite in terms of operator notation, okay? And we want to solve this system. The first idea is to decouple the system. And we'll do that by eliminating x, okay? And how do we do that? So look at the factors in front of the x. So if we take equation 1 and multiply it, or operate on with d plus 1, and we take equation 2 and operate with d minus 4, we'll get the same terms, okay? We'll get the same terms here, as you'll see. This is the first equation operated on, and here's the second equation operated on. And of course, because we're dealing with constant coefficients, the operators commute. That's an important point, okay? The operators, you could switch around these operators because we're dealing with equations with constant coefficients. And so this would cancel that, and you'll be left with this term minus this term here, okay? And let's not forget the right-hand side. We operated with d plus 1 on the right-hand side, and this d is with respect to t, okay? That's what these primes mean. Okay, that is the only independent variable. So from the first equation operated with d plus 1, we get that, and d minus 4 operated on the second equation, we get that. And so we get these terms here, and simplifying we have now this third order differential equation that's non-homogeneous. How do we solve that? Well, we have constant coefficients, so we're going to use this, we're going to take the auxiliary equation, we're going to use the method of undetermined coefficients at the end of the day to solve this, because we also have a polynomial term here, and we know that the method of undetermined coefficients works for that. Okay, and so here's our auxiliary equation. We solve it. We get these three roots. They give us the complementary function here. And now for the non-homogeneous part, we use undetermined coefficients. And now we have to be pretty careful here, because m1 was 0. When you plug that in to the exponential, you just get a constant. Now, for the method of undetermined coefficients, with a polynomial, you would have at squared plus bt plus c. But because of that duplication with that final c and this, what do we do? What's our trick? We use that multiplication rule, and we multiply by t. Okay. Once we multiply by t, none of these terms are duplicated now in the complementary function. All right, so we have our form for the particular solution. Left-hand side is coming from the original kind of problem here. And now right-hand side is our form of the particular solution plugged into the differential equation. Okay, plugged into this differential equation. So if we, take the derivatives and multiply by 4 here, we get this right here, and we match terms. Okay, so this 12a has to match the coefficient of the t squared. That's that. This 8b has to match the coefficient of this t. That's that. And finally, this constant term has to match the constant term here, which is actually just plus 0, right? And so that's, we solve, we get ABC. And here goes then our solution for, our general solution for y, okay? Notice we have 3 constants there because it's a third order differential equation, okay? And this is something that's not a coincidence that we're getting, to decouple the equations, we're going to higher order, okay? There is no free lunch. So now we could do this for x. We could, subtract out now y. Right? You could see if you operate 2 with d, you get a d squared here and a d squared there, and you could subtract them. And that's precisely what we're going to do. So for x, we look at that relation there. These d squareds fall out. We get this on the right hand side. We're operating D on 0 is just 0, doesn't matter. Okay, and we get this and we simplify and we have that. Now we do the same thing. We're going to use the method of undetermined coefficients. Our auxiliary equation is here with these two complex conjugate roots. We get that. Now what form of particular solution do we use? We use this form here. Okay, and notice this, we're solving this different, we're solving this independent of the previous y. So one doesn't think like, hey, I don't want to duplicate the terms of this y up here this y particular or the previous. It's completely independent. What you're doing for x is independent. Okay, now we're going to plug in our solutions into the equations at the end to kind of reduce the degrees of freedom to show where they depend on each other. But for now, we treat x and y completely independently. Okay, we've decoupled them. Okay, and so we have this form where there is no duplication with the complementary function for x. Okay, doing the straightforward method of undetermined coefficients, we get these three equations, which we could solve for E, F, and G and get this right here. Okay, for x, here's our particular solution and here's our complementary function. Okay, and you see two constants there. Now C1, C2, C3, C4, C5 are not independent. As we've seen earlier, we have to go back and plug in one of the solutions into one of the equations. Okay, or we have to plug in both solutions into one of the equations because, well, each equation depends on both variables. Okay, and so we're going to figure out the dependence between these constants. So we do that. We're going to take the solution for x, which is this, and the solution for y, which is this. And of course it gets messy, but you plug them into, say, 2. And why do we choose 2 rather than 1? Because, well, this is a first order equation, so it's, if we could be spared taking multiple derivatives, why not? And we get this equation there, combined terms. Well, this means each one of these is 0, right? Because sine and cosine are not identically 0 on some interval. So we know then these coefficients have to be 0, and we reduced our degrees of freedom now. Okay, so we could solve for C4 and C5. And why C4 and C5 instead of like solving for other ones? Well, these are the last ones, right? So why not? And now we substitute for C4, we substitute what we just found here. So C2 and C3, these show up in Y. And C5, we substitute in here. Okay, and again, we could have chosen equation 2 and gotten similar relations. At the end of the day, you've reduced the equations you've reduced your solution to 3 degrees of freedom, C1, C2, and C3. And we now have this solution, okay, for x and y, and they respect both equations, okay, and they respect the degrees of freedom in those equations.